we truly observe reality or just what our theories let us see? That is the puzzle behind the Theory Ladenness Paradox, which suggests that all observations are shaped by the theories we already believe. In science, we often imagine data as objective and neutral, but in practice, what we notice, how we measure it, and how we interpret it are all filtered through our prior knowledge and expectation. For example, before the concept of bacteria existed, scientists looking through microscopes may have literally seen bacteria, but without the theory, they did not recognize them. This means our perception is not a pure reflection of nature, it is theory-laden, shaped by the mental frameworks we bring to the table. So what does this mean for science and discovery? It implies that even the most objective observation may be subtly biased because you can only find what you're prepared to look for. The instruments we design, the phenomena we test, and the patterns we seek are all guided by our current models of understanding. Analogy: it is like wearing colored glasses. You think you're seeing the world as it is, but everything is tinted. The Theory Ladenness Paradox challenges the idea of a clear-cut division between theory and data and reminds us that scientific breakthroughs often happen not just by seeing new things, but by learning to see old things in new ways. Why do our observations in science often reflect the theories we already hold, shaping not only what we notice, but even what we consider data? From telescope images to particle collision graphs, every measurement is filtered through instruments, procedures, and interpretive schemes rooted in existing theoretical frameworks. This entanglement means that what scientists see is rarely a raw window onto nature, but a constructed picture guided by prior expectation. So far, so good, until we confront how deeply this conditioning runs. Experiments designed to test competing hypotheses typically presuppose the very phenomena they aim to validate. Data processing pipelines flag events that align with theoretical signatures while discarding noise that might contain novel effects. As Thomas Kuhn argued, anomalies accumulate unnoticed until a paradigm shift forces researchers to re-examine their instruments, methods, and even what counts as legitimate evidence. At its core, the paradox hinges on the dual role of theory as both guide and gatekeeper. Theoretical models determine which variables are measured, how instruments are calibrated, and which statistical thresholds define significance. For example, early 20th century spectroscopists hunted for spectral lines predicted by quantum models. Lines outside that pattern were often dismissed as only when the theoretical lens changed did researchers revisit archive data and uncover previously ignored signals. Yet even this insight conceals further layers. Instrument design itself encodes theoretical commitments, the choice of wavelength range in telescopes, the bias settings in electronic detectors, or the chemical staining in microscopy, all reflect expectations about where and how phenomena should appear. When a novel effect lies outside these design parameters, it remains undetected until someone intentionally looks in a new way, often requiring not just fresh theory but new hardware. At even finer scales, human cognition compounds the effect. Scientists tend to trust measurements that fit their models and question outliers, attributing them to error rather than insight. Collaborative review processes can reinforce prevailing views, as dissenting data may struggle to pass peer review filters tuned to conventional interpretation. Only when a critical mass of anomalous findings accumulate, sometimes driven by entirely new generations of researchers, does the community recalibrate its observation. In essence, the Theory Ladenness Paradox reminds us that scientific observation is an active, theory-driven act, not a passive recording of reality. It challenges the ideal of pure objectivity, showing that what we see in nature depends on the conceptual lenses we bring. Like other deep paradoxes, from the hysteresis paradox's history-dependent outcomes to the quantum retroactive realism's future-shaped past, this phenomenon urges us to remain vigilant about our assumptions, continually questioning whether our theories are illuminating truth or simply coloring our view of it. The Theory Ladenness Paradox holds that our observations are influenced by the conceptual frameworks and theories we already accept. What scientists see in experiments is filtered through instruments, terminology, and interpretive lenses that reflect existing models. Consequently, data do not speak for themselves, but acquire meaning only in the context of theoretical assumptions. This challenges the ideal of a purely objective, theory-neutral observation. Early astronomers interpreted sunspots differently depending on whether they believed the sun was perfect and unblemished or subject to change. It is like wearing tinted glasses that subtly color every scene you look at, even though the world itself hasn't changed. Neutral observation assumes that raw sensory input can be recorded without bias, providing a foundation for theory building. Theory-dependent perception, by contrast, asserts that what counts as an observation is shaped by what instruments detect and researchers expect to find. In this view, observations are not independent checkpoints but emerge from the interplay of stimuli and interpretive schemas. Thus, the line between theory and data becomes blurred. In early spectroscopy, lines in atomic spectra were cataloged only after Bohr's model suggested discrete energy levels, guiding which features were deemed significant. It is like a treasure map that highlights features you're already inclined to seek, causing you to overlook unexpected landmarks. At the cognitive level, humans organize sensory input into patterns based on prior knowledge, a process psychologists call perceptual schema. These mental frameworks determine which aspects of a stimulus are grouped, suppressed, or emphasized. In scientific practice, researchers apply analogous schemas when selecting data points, labeling peaks, or discarding noise. As a result, raw signals are transformed into meaningful observations only through theory-infused interpretation. A seismogram's tiny wiggles might be classified as background noise unless a geophysical model predicts microseismic tremors at that frequency. It is like sorting a deck of cards by suit. The same shuffled cards can look very different depending on which suit you focus on. Scientific instruments themselves embody theoretical assumptions in their design, calibration, and data processing algorithms. Choices about sensor sensitivity, sampling rates, and signal processing thresholds reflect beliefs about relevant scales and phenomena. These built-in filters shape the output and determine which signals are recorded as data. Consequently, instruments do not passively record nature, but actively shape what appears to be observed. Electron microscopes tuned for high resolution may miss larger, slower processes that a light microscope would reveal, directing attention towards subcellular structures over whole cell dynamics. It is like a camera lens with a fixed focal length. You can only capture sharp detail at certain distances, while everything else remains out of focus. Scientific communities reinforce theory-laden observation through shared training, publication standards, and peer review, which uphold prevailing paradigms. New findings are judged against communal expectations, and data that fit the paradigm are more readily published. Anomalies may be dismissed or reinterpreted rather than prompt a revision of underlying theories. Thus, collective practices institutionalize theory dependence in observation. The initial disconfirmation of the Michelson-Morley experiment was resisted because the ether theory dominated physics until relativity reshaped communal beliefs. It is like a choir where singers tune to a leader's pitch. Any note that deviates is subtly adjusted to match the group's established key. Theory-laden observation can produce nonlinear feedback loops where initial expectations lead to selective data gathering, which then reinforces those expectations. Confirmation bias drives researchers to notice data that confirm hypotheses and overlook contradictory evidence. Over time, this can magnify minor theoretical predictions into perceived major effects. The paradox thus illustrates how subtle cognitive biases can distort the scientific record. In early cold fusion experiments, anomalous heat readings were amplified by the researchers' belief in tabletop fusion, leading to premature claims. It is like tuning a radio to your favorite station so strictly that you interpret static as part of the song because you expect to hear it. If observations are inherently theory-laden, then testing theories against pure data becomes problematic. Scientific realism, the view that theories can accurately describe an objective world, must account for the interpretive role of theory in shaping that world. Researchers must therefore design critical experiments that minimize interpretive biases and employ multiple independent methods. Recognizing theory dependence leads to more robust strategies for theory comparison. Cross-metallating climate models using satellite, ground-based, and proxy data reduces the risk that any single instrument's biases will dominate conclusions. It is like verifying a story by comparing eyewitness accounts, security footage, and forensic evidence rather than relying on a single testimony. Eliminating theory-laden biases is difficult because even blind protocols and automated analyses rely on parameter settings and threshold choices. Reproducibility efforts must therefore document not only raw measurements, but also all interpretive decisions, software versions, filter settings, and analyst judgments. However, capturing this interpretive metadata remains an ongoing challenge in experimental practice. Without it, reproducing results can inadvertently reproduce the same biases. Genome sequencing pipelines can yield different variant calls depending on alignment algorithms and quality filter cutoffs, affecting downstream biological interpretations. It is like baking the same recipe but leaving out the oven temperature and mixing time. Others can follow the steps but never replicate the exact cake. Advances in AI and automated reasoning offer prospects for more theory-based data analysis by tracking and reporting decision points. Developing frameworks for interpretation provenance could make theory dependence explicit and quantifiable. Interdisciplinary dialogues between philosophers of science and experimentalists can foster methodologies that mitigate theory-induced blind spots. Ultimately, embracing the theory ladenness paradox may lead to more reflexive and self-correcting scientific practices. Emerging platforms that log every data processing step in real time enable full audit trails of how raw signals become published findings. It is like using version control in software development to track every code change, revealing how each tweak shaped the final program.